Functional connectivity is defined as statistical dependence between brain signals at different parts of the brain. It is crucial for understanding brain function, cognition, behavior, and it is typically estimated between many pairs of brain areas, as here, electrodes in different brain areas, resulting in a 2D matrix like this one, where each bin corresponds to that statistical dependence measure between those two brain regions. Using a sliding window approach, akin to how movies are made up of pictures put together, functional connectivity dynamics between all pairs of brain regions can be extracted as 3D data, so across time. But what are the measures for these statistical dependencies? Phase coupling and amplitude coupling are two important brain connectivity measures used when analyzing electrophysiological data, that is, fast oscillatory signals. Phase coupling quantifies the similarity between the rhythms of signals over time, that is, how in synchrony their phases are, while amplitude coupling measures the strength of those signals over time, not necessarily in sync. A previous study showed that static amplitude coupling and phase coupling relate only in the baseline organization, that is, functional connectivity at resting state, but have distinct responses to stimuli. We wanted to investigate this further, but with more focus on the dynamic functional connectivity rather than the static. Studies have reported that functional connectivity dynamics are made up of a mixture of several hidden brain states. Those are specific patterns of neural activity. So our aim was to disentangle these components, these states, of amplitude coupling and phase coupling dynamics to better understand how they relate. To do this, I developed a pipeline in MATLAB for extracting brain states from functional connectivity dynamics data. This was done through the hidden Markov model method. A brief introduction. A hidden Markov model takes a series of observations that give clues to what unobserved state gave rise to those observations, such as someone reporting by phone if they're happy or sad, their mood, and the listener inferring whether it is rainy or sunny, the weather, where the color is, based on that mood report. So given a series of mood reports, the HMM could infer the most likely weather patterns, given that calculated probabilities based on the data. The pipeline uses the hidden Markov model to disentangle the data into brain states. So it takes this data and labels it. So each time point is labeled with a brain state. Once we had the method of extracting these states, we were able to compare the average functional connectivity data across time associated with each state. That is, the static functional connectivity of that state. And then we were able to get the spatial similarity, that is, the correlation between all states of amplitude coupling and phase coupling data, resulting in a matrix like this one. We repeated this with C-scored data. We use C-scored data because it subtracts the average from the data, thus discounting the baseline organization presumed to be the link between amplitude coupling and phase coupling. So it was a good comparison. In a nutshell, our question was, what is the relation between amplitude coupling and phase coupling in functional connectivity dynamics, primarily those states? The findings in this study will help connect different brain study literature that use phase coupling or amplitude coupling and complement each other's findings. This will enable us to better understand the brain.